Okay, so we are going to talk about carbon chains. So for many people, getting up at 5 a.m. on a Saturday morning is not exactly the best way to start a weekend. But if you play hockey, you have to practice when your team is able to get some ice time. In the winter, this can mean getting up hours before the sunrise and hopping into a cold vehicle to drive to the arena. Although this does not sound like a story about chemistry, many of the products involved in early morning hockey practice are made up of a large number of carbon-based compounds. The gasoline used to fuel the car, the plastic used to manufacture the hockey equipment, the synthetic material used to make the uniforms, the medications like aspirin, Tylenol, and Advil players used to treat minor injuries, and the breakfast quickly eaten by players on the way, and even the molecules that make up the body are all carbon-based compounds. So a carbon-based compound is a compound primarily made up of carbon atoms. Organic chemistry is the study of compounds composed of carbon. So most of the molecules in all living things on Earth are carbon-based. The strong presence of carbon-based compounds in organic matter is why the study of these compounds was originally called organic chemistry. Fats, proteins, and sugars are all made up of carbon chains. So why is carbon such an important building block of living things and non-living things on Earth? Well, to answer this question, you need to look at the carbon atom itself. So the carbon atom. So when looking here at the Bohr model, we can see that it's got 4 bonding places. Carbon's first valence electron energy level is full. Okay, but its second energy level can hold 8 electrons, but it only has 4 electrons. So it needs to bond with 4 other atoms to become stable. Compare that here to this Lewis dot diagram. So again, there's 4 bonds, 4 bonding places, and here with the molecular model, we've got 4 more bonding spots. So recall that an atom is most stable when the outer energy level is filled with electrons. Carbon has 4 valence electrons and 4 empty spots in its outer energy level. Carbon needs to form 4 bonds with other atoms to become stable. Compare a carbon atom to other atoms like hydrogen. Hydrogen has only 1 electron in its first energy level. Therefore, it can only bond to 1 other atom to become stable. And here we've got our Lewis dot diagrams and molecular models for that. So hydrogen only requires 1 electron to fill its outer energy level. This means that it bonds to only 1 other atom to become stable. Because carbon needs to form 4 bonds to become stable, it's able to form many bonds with other atoms. This gives carbon the ability to produce a large variety of compounds. For example, here we have methane, which is CH4. So the carbon is bonded to 4 atoms, the hydrogen, so it's stable, and each hydrogen is bonded or attached to 1 atom, the carbon atom, so they're all stable. If we look at ethane here, C2H6, again, each hydrogen is bonded to 1 atom, the carbon atom, so they're all stable. And each carbon atom is bonded to 4 atoms, 3 hydrogens and 1 carbon, so they're all stable. Note here that carbon will often bond with another carbon to form a carbon chain. Compare this again to propane, where each chain has different properties that depend on how many carbons within that chain. So here we've got 3. This middle carbon here is attached to 2 hydrogens. So by adding other carbons to the chain, you get a new compound with slightly different properties. The carbon chains made for plastics consist of thousands of carbon atoms. So since Wooler's discovery, scientists and technologists have dedicated an immense amount of time and effort in investigating and designing synthetic organic molecules to develop products. So take a look at these molecules and their associated products. So butane, butane is often used in barbecue lighters. Ethene is a starting compound when used to produce polyethylene, which is used to make plastic bags, and ethine, which is the starting compound for PVC, which is used to make grain gear. So a few observations you might make while looking at these compounds are as follows. The only atoms involved are carbon and hydrogen, and organic molecules contain single, double, or triple bonds. The organic molecules that you will be exploring in this chapter are all a part of a class of organic molecules called hydrocarbons. This name approximately appropriately describes the molecules that belong to this category because they're all made up of only carbon and hydrogen atoms. Hydrocarbons are the simplest group of organic compounds. To understand organic chemistry, you first need to have a good grasp of hydrocarbons because all other organic molecules are very similar. So a hydrocarbon is an organic molecule containing only carbon and hydrogen atoms. So alkanes, propane, commonly used for barbecuing, is an example of the simplest group of hydrocarbons. These compounds have only single bonds between the carbon atoms, and the family of molecules is called alkanes. So alkanes is a hydrocarbon that consists of only carbon atoms and single bonds. So each carbon is in an alkane is bonded to four other atoms. As a result, the number of hydrogen atoms bonded to the carbon atoms in a hydrocarbon alkanes have the general chemical formula of CnH2n plus 2, where N represents the number of carbon atoms in the hydrocarbon. So, for example, here we have propane, okay, which is C3. So H, 3 times 2 is 6, plus 2 is 8, okay? So that's how I know that that's an alkane. So alkanes, here we have a bunch of examples and how they go together. This is actually in your booklet, so take some time to look and understand how these are all kind of related. So the alkanes depicted in the continuous chain alkanes because the carbon atoms form one chain of consecutive carbon atoms. These hydrocarbons can be represented in several ways. So a chemical formula, which shows the number of carbon and hydrogen atoms in a molecule, and includes chemical symbols. The Lewis dot diagram, showing the sharing of valence electrons between hydrogen and carbon atoms as pairs of dots, includes chemical symbols. The complete structure diagram, which shows covalent bonds between atoms as a short line, and it includes chemical symbols. And then a condensed structural diagram, which shows carbon-to-carbon bonds, but omits the carbon-hydrogen bonds, including chemical symbols. So continuous chain alkanes. An alkane consists of one or more simple chain of carbon atoms. A complete structural diagram is a diagram of molecules that use short lines to show the bonds that exist due to the sharing of pairs of electrons between atoms. And condensed structural atoms, the diagram of molecules that use short lines to show carbon bonds that use chemical formula and carbon-hydrogen bonds. All right, so if we look here, these are the various diagrams for propane, so which is C3H8. So we've got a Lewis dot diagram, a complete structural diagram, and a condensed structural diagram. So naming continuous chains alkanes. So yeah, there are under 500,000 compounds that do not contain carbon. By comparison, there's an excess of 10 million compounds that do contain carbon. Each day, new organic compounds are being added to this huge list, just as each new compound has its own unique structure and set of properties, each compound needs its own characteristic name. People, such as pharmacists, need a systematic way to name these compounds. As a result, scientists use systems that allow them to accurately describe the size and structure of each organic molecule. The International Union of Pure and Applied Chemistry, also known as IUPAC, have developed a system of naming organic compounds. The system involves the use of prefix and suffix to convey a specific meaning. Prefixes indicate the number of carbons within a carbon chain, and suffixes indicate the family of molecule that it belongs to. Different families have different molecular structures. So a prefix is the first syllable in the name of an organic molecule that indicates the number of carbon atoms in a molecule, and the suffix is the second syllable in the naming of an organic molecule that indicates the family of organic molecule. So prefixes for continuous chains. Here are all of the prefixes up to 10. So to name an alkane, you need to match the correct prefix that describes the number of carbon atoms in the longest continuous chain to the suffix for the group. Alkanes have single bonds between the carbon atoms and are described by the suffix -ane or ane. So examples of naming continuous alkanes. So here we have the complete diagram structure. We've only got one C, okay, bonded to 4H, all single bonds. So this molecule has only one carbon atom, therefore it is called methane. Okay, we've got 3 here. This molecule has 3 carbon atoms in the chain, therefore it is named propane. So here are common alkanes and their applications. So methane is gaseous fuel, ethane is a gaseous fuel as well as a starting compound for plastics. We've got propane and butane again. These are gaseous fuels. Pentane, hexane, heptane, and octane. These are all solvents, some of which are liquid fuels as well. And then nonane and decane are also liquid fuels. Here for heptane and octane, these are ingredients for jet fuel and diesel fuel. So simplified structural diagrams. So the structure of diagrams of many compounds can become very complex and difficult to draw. Scientists have developed shortcuts to make drawings and reading these structures easier. The following shows the increased simplification starting with the molecular model and ending with the line structure diagram for pentane. So a line structure diagram is a diagram of a molecule that only uses short lines to show the bonds between the carbon atoms. The diagram for the molecular model of pentane communicates the most information, right here, but it is the most difficult to draw. The line structure diagram is easier to draw, but it communicates the least amount of detail. So most students prefer the complete structural diagram or the condensed structural diagram because they provide a compromise between detail and ease of drawing. So branched alkanes. Hydrocarbons do not always form continuous chain alkanes. Carbon atoms are like building blocks, and there are a variety of ways that they can be arranged. They often form long chains with smaller carbon branches attached to them. This kind of hydrocarbon is called a branched alkane. So a branched alkane is an alkane consisting of a long chain with smaller carbon branches attached to it. So branches of alkanes can become complex. Each new branch attached to the parent chain contributes to a molecule's uniqueness and its own set of properties. The main reason so many organic compounds exist is that there are so many possible locations for these branches. So here we have the parent chain, which is made up of 5 carbons, and then a branch made up of 1 carbon, and then this branch here made up of 2. So naming branched alkanes. IUPAC has developed a system for naming branched alkanes. To name a branched alkane, you need to follow these steps. First, you need to find the longest continuous chain of carbon atoms in the molecule. Circle this chain and label it the parent chain. Name the parent chain as though it was a continuous chain alkane. For example, if the parent chain consisting of 6 carbons, it is called hexane. Then we need to find all of the branches and circle them individually. Each branch is called an acyl group, and we need to name each group with the prefix that corresponds to the number of carbons in that group, and then end with the suffix YL. So for example, 1 carbon branch is called methyl, and 2 carbon branch is called ethyl. So to communicate where in the branch the parent chain is, the number of carbons on the parent chain starting at the end nearest to the first branch, and we assign each branch an appropriate number. So for example, 2-methyl means that there's a methyl group on carbon 2. Then we need to communicate how many of each branch type exists in the molecule. So to do this, we need to refer to the following table. So an alkyl group is a branch of a larger molecule consisting of an alkaline with 1 hydrogen removed. So if there's 1, there's no prefix: di, tri, tetra, penta, hexa, hepta, and octyl. So for example, dimethyl means that you have 2 methyl branches in the chain. So if we put the name together, starting with the alkyl groups in alphabetical order and ending with the parent chain. So here we go. Name the following compound. So now we need to find the longest chain and name it. Be aware that the longest chain may not be in a straight line. So in this case, if we were to go in a straight line, I would only have 1, 2, 3, 4, 5, 6 carbons in my parent chain, but I actually have a parent chain of 1, 2, 3, 4, 5, 6, 7 carbons, okay? So it's very important that we find the longest chain and label that the parent chain. So the longest chain has 7 carbons, therefore the parent molecule is called heptane. Next, we need to find all the branches and name them. So we have a methyl branch, a second methyl branch. We have an ethyl branch here because it's got 2 carbons. Our parent chain is still there. So this molecule has 2 methyl branches and 1 ethyl branch. Then we need to number the parent chain. So this methyl branch is closer to an end than this ethyl branch. So we start numbering at this end of the chain. So 1, 2, 3, 4, 5, 6, and 7. So this molecule has a methyl branch on carbon 2, a methyl branch on carbon 3, and an ethyl branch on carbon number 4. Now we need to organize branch types and numbers. So because there are 2 methyl branches, one on carbon 2 and one on carbon 3, this becomes 2,3-dimethyl. Because there is one ethyl branch on carbon number 4, this becomes 4-ethyl. No mono prefix is required. So this is dimethyl because it's saying that I've got 2 methyl branches, one at 2 and one at 3. So we need to put the name together. So the parent chain is heptane. Branches, we've got 2,3-dimethyl and 4-ethyl. So we place the branches in alphabetical order and end with the parent chain. We do not include prefixes, for example, di and tri, when alphabetizing. Therefore, the name of the compound is 4-ethyl 2,3-dimethylheptane. Note that there are no commas between the numbers and hyphens between the numbers and the letters. Sorry, note that there are commas between the numbers and hyphens between the numbers and the letters. So the importance of IUPAC naming system. As we saw in that example problem, a systematic approach is required to properly name an organic compound. You may wonder why so much effort is put into this process. Why not just use a simple chemical formula for this compound? The answer is that a simple chemical formula for the compound, so an example problem there, C10H22, could mislead you into thinking that this compound was decane, a continuous chain alkane with a much simpler structure. So due to the fact that carbon atoms can form 4 single bonds, there are many possible arrangements for a given number of carbon and hydrogen atoms. The IUPAC naming system makes sure that you correctly identify each compound. Thanks for listening.